If you're going to use occlusal design, then you need to be aware of really the consequences of that. So we want that occlusal issue. It makes it easy for the chewing component of what we're doing. But if you want a very steep angle, then what we have to do is that we have to adjust the toughness. So we need a higher toughness material, the sharper that system is, because that stress is going to be concentrated at that fissure point. So therefore, the higher the degree of sharpness, then the tougher material that we need to do. The near final area I want to look at is this problem of chipping. Now, chipping is becoming, as I said, a major disease in the case of zirconia systems. And the chipping is primarily in the porcelain that's attached to the zirconia. And this is just one example of the case of an implant-supported abutment structure, a crown placed on an abutment. You can see this big chip. Other examples that are taken from the literature, you can see this large chip that is here in these systems. Now, this chipping is really taking place very, very frequently, and in fact more frequently than some of the values that people are talking about, because often it's smaller chips, but the big ones are ones that people cannot ignore. There was this report by Christensen out of the group at CRA in the United States, and they said the blue line is the porcelain fused to metal in terms of chipping and failure. The red line here is the value for the porcelain fused to zirconia. So you can see that there's a factor of 3 to 5 increase in the extent of chipping in the case of the porcelain fused to zirconia. And it's occurring both in the normal veneered and then these are pressed systems as well. But it's not occurring uniformly. Some materials, for instance, here we have two different crown systems. We have the Noritake here, very small incidence of chipping. Whereas here we have, for instance, the Empress material. Again, we have very high incidence of chipping. So what is it about these different materials that also influences these degrees of chipping that occur in these systems? So there are two possibilities in terms of this chipping. One is that the chipping can be associated with this transformation at the boundary between the tetragonal and between the zirconia and the porcelain. So the zirconia is transforming, and then this can give rise to this. Or it's occurring within the porcelain. Then the question becomes, well, what is unique about porcelain for zirconia? Why is it different? We've had porcelain for various ranges of metals. We have porcelains for alumina. We have porcelains for titanium. Why is the porcelain for zirconia so different that it introduces this substantive amount of chipping? Now we can have this transformation. We have this process that when we heat the zirconia up to typically of 20 to 100 to 200 degrees centigrade, we get rapid transformation of this material in the surface. So for instance, you never autoclave zirconia components before placing them in the body. It triggers this transformation very dramatically, and this then causes a weakness or reduction of strength. But how do technicians make these systems? They take the zirconia, they put a wet layer of porcelain which they build up, they hold it under the drying conditions in the furnace, just below the furnace, till it dries out, then they put it up into. So that is perfect examples of a case where it will trigger or start to trigger transformation. And it does destabilize the surface. And we've just now published a couple of papers showing that this does cause this transformation problem. But I don't believe that is the cause of the chipping. Why? Because the chipping is occurring within the porcelain. It's not occurring at the interface, or rarely do we see it at the interface. So, if I summarize what is going on in porcelain systems, chipping does occur. We acknowledge that in all systems, but the incidence is such that it has not been a significant problem in Procera-based systems, porcelain on Procera, porcelain on Insula. It has not been a major problem in the case of porcelain fused to metals. It's only occurring with the veneering porcelain and does not usually occur at the porcelain zirconia interface. So the question, what is unique about the porcelain on zirconia? Sorry, this is a busy slide, but it's trying to convey some features. So in the case of zirconia porcelain, we have the coefficient of thermal expansion is about 8 to 10 parts per million. Or 8 to 10 by 10 to the minus 6, 30 degrees centigrade. The elastic modulus, like most porcelain, is between about 70 and 80. The strength is about 170 to 100 megapascal. The fracture toughness is typically between 0.7 and 1. And the thermal conductivity is relatively low because it's a amorphous structure. That's why we have glass windows and things like that, because they're poor thermal conductors. Now, when we go to the zirconia, the framework of this system, what do we find? Well, of course, the CTE is a little bit higher. The elastic modulus is much higher because it's a crystalline ceramic system. And the thermal conductivity is a little bit higher, but not much from that of the porcelain, 2.5 watts per meter Kelvin. We go to compare it with, say, alumina. In alumina, we have a CTE that is lower. With the porcelain, we have virtually the same elastic properties, same strength, same fracture toughness, same thermal conductivity. But now if we have a look at the alumina framework, it's got a lower thermal expansion coefficient, and we also have a very much higher elastic modulus. But look at the thermal conductivity. The thermal conductivity of this material is 27 versus 2.7 in the case of the zirconia. So there are very significant differences in the thermal conductivity. So this can give reason for the basis of the chipping. There is a CTE mismatch, but again, the CTE mismatch is relatively minor, and there are tempering stresses, and the tempering stresses are stresses I will just talk about in a minute. And I would argue that the reason for the chipping is that in the process of production, we are treating zirconia as we treat, for instance, a metal-based systems or alumina-based systems. But the zirconia has a very poor thermal conductivity, so it does not cool down as quickly.